Hey everyone, welcome to this lesson where we are going to deep dive into an exciting new feature in Apache Spark 4.0, which is stateful streaming processing. But before we get into the specifics of this new feature, let's quickly talk about a fundamental concept in stream processing. What exactly is stateful processing? This is a fascinating concept, and personally, when I'm interviewing candidates for senior roles, I expect them to have a strong understanding of it. Not necessarily in Apache Spark, since that's a brand new feature, but there are other major tools that support stateful streaming, like Apache Flink and Kafka. Alright, enough talk. Let's dive in. Imagine you're processing a continuous stream of data. You're going to need a streaming engine. That can be Apache Flink, Kafka, Spark, Kinesis, and so on. You have naturally a sequence of inputs for your streaming applications, say clicks on a website, sensor readings from IoT devices, or financial transactions. The engine can take some actions in each data point and output the results. In stateless processing, every piece of data is handled independently. The system doesn't remember anything about past events. Let's say we are measuring the temperature in multiple areas of a city, and we know that there are some broken sensors that output nonsense values. If we know that the temperature in that city is never negative, we can filter out negative values. So we have a very simple filter in our engine that is this temperature positive? It looks at one value at a time, makes a decision, and moves on. It doesn't need to know about previous measurements. Another example is if our application needs to receive temperatures in Celsius and output those temperatures in Fahrenheit. The engine will just perform this action in each data point and output a result without caring much about previous data points. Another simple example is a streaming pipeline that receives JSON files as input and transforms them into another format like CSV, Parquet, or Delta. Let's head to the last example. A credit card company that wants to filter only successful transactions to do something with them. Again, it's just a simple filter, and the engine will evaluate each data point at a time. If it's a failed transaction, it is discarded. If it is a successful transaction, we output it for downstream tasks. Now, let's increase the complexity of our problem. Imagine this credit card company wants to detect suspicious activities and they decided to block a credit card if the user tries a wrong password more than 3 times in less than 10 minutes. See how it is more complex than just filtering values? The solution for this problem is clearly a stateful streaming processing. Stateful processing is different than stateless processing because here the system needs to remember information from past events to process the current event correctly. This memory is what we call state. Here, we need to differentiate users and the engine must be able to identify them. Let's imagine 3 users: pink, yellow, and green. We already know we need to detect wrong passwords in a 10-minute window. Let's set all the wrong password counts to 0, and this is the state of our application. Got it? It is called the state of the application. Let's start our streaming. First, the green user performs a successful transaction with the right password, so nothing to change in the state of the application. Then, the pink user also got it right, so our state remains the same. Now, the yellow user tried a wrong password, so our engine will update the state of the application, incrementing the counting of wrong password for the yellow user, going from 0 to 1. The pink user also got it wrong this time, so let's update its state as well. Then the green user gets it correct. Nothing to do here. The yellow user gets it wrong, so now we update yellow user's wrong password from 1 to 2. The pink user got it right this time. So it looks like it was just a usual mistake at the first trial. It happens. And finally, the yellow user got it wrong again, 3 times in a row in the same 10-minute window. So now our engine has to trigger an output, a signal to block the yellow user. Historically, managing this state efficiently and reliably in distributed streaming systems has been a challenge. And that's precisely where Spark's feature for stateful streaming and now the new transformWithState operator come into play. They provide powerful tools to handle this memory for you. Let's see how Spark 4.0 transformWithState makes it easier and more powerful than ever to build these kind of applications. First, we should know that stateful streaming is now available with different syntax for each language. You can use transformWithState if you're using Java or Scala, but you need to use transformWithState in pandas if you're using Python. When we are building a streaming query with transformWithState, there are typically four main components we work with: stateful processor, output mode, time mode, and initial state. Let's see what they are. First, we have the stateful processor. This is where our custom logic lives. It defines how input data interacts with state and what is the output. The output mode can be something like append or update. It defines how the results are written to the sink. Now we have time mode. This is out of the scope of this video, but if you want to master real-time data streaming, you should study a bit about time modes and time windows. Lastly, we have the initial state. We can provide an optional data frame to pre-populate the state before any stream starts. Alright, let's jump into the code to see it working. Let's build a real-time fraud detection application for the credit card company we discussed earlier. Don't worry about following along with the code right now. Everything will be available in the course GitHub repository for you to explore later. First, let's talk about our environment. We're using a single node Databricks cluster with 16 gigabytes of memory and 2 cores. The access mode should be set to dedicated or single user, and we're on Databricks runtime 16.4 LTS. This runtime is great because although it shows us Spark 3.5 here, we already have access to some Spark 4.0 features, including the stateful streaming capabilities. Alright, let's go to our notebook. The first step is handling the imports. The most important of these are the stateful processor and stateful processor hero from pyspark.sql.streaming, which are the core building blocks of our application. We also need to define some key configuration variables: the catalog and schema for our tables, names for the incoming orders table, and the output block table. Also, a 10-minute window for our logic. Here I have a 1-minute window because I was testing, but let's set it to 10 minutes. Crucially, we also define a checkpoint directory. This is essential for any Spark streaming application, as it's how Spark saves its progress. If the stream stops, it knows exactly where to pick back up. Finally, we'll switch the state store provider to the RocksDB based provider. I found it to be more flexible, and it's also a recommended practice by Databricks. Now for the heart of our lesson: the fraud detector processor. This is a Python class that extends the stateful processor object, and it's where we'll define our fraud detection logic. The stateful processor contains 5 methods that we can use inside it. The init method that will create and initiate the state variables. The handle input rows that will basically be the processing logic that we need to define for each row. The handle expire timer. This is out of scope of this video, but we can talk about it a bit later. The close method to perform some cleanup after processing, and the handle initial state to pass the optional data frame that will pre-populate our state before the stream starts. But in this demo, we are just going to use 2 of those methods: init and handle input rows. The init method is where we initialize our state variables. The method receives a handle, which is our connection to Spark state management system. We'll define 3 state variables: For each variable, we need to define a schema. We're passing here a Spark way of defining schemas. So for failed attempts, it's going to be integer type because it is the count of wrong passwords. The first error timestamp is timestamp type, and the is blocked is a boolean. Note that the getValueState has two parameters. The first one is the state name, and the second one is the schema of the variable. It's worth mentioning that we have not only the getValueState, we also have the getListState and the getMapState if we want to have a map as a variable. That will work very similar to a Python dictionary. But here we are using the getValueState because each variable is just one integer, a timestamp, or a boolean. We are not using lists or maps here. Okay, next we have the handle input rows method, and this is where the magic happens. This method is called for each new batch of data that arrives, grouped by user ID. You can see that the key is a tuple. We are just retrieving the first element of it to be the user ID. The key is the same key you are going to use in your group by clause. Okay, let's iterate over the input rows. But before that, let me add some print statements here so you can understand what are the PDF and the rows here. Just so you know in advance, PDF stands for Pandas Data Frame. First, we retrieve the event time, which is a column of our input data frame. Actually, let's have a look at it. In the next cell, we can see the data that we're going to stream. We have four columns: user ID, which is a string, value, which can be the purchase value and is a float, a is password correct column, which is a boolean, and the event time, which is a timestamp. So after retrieving event time, we're going to check if the user is blocked. In case the user is blocked, we don't want to process his request. So we just yield an empty data frame and have a continuous statement there to jump to the next request. In case the user is not blocked, then we proceed to the processing. We want to check if the password is correct. If so, we clear the state. This is for the cases when someone misses a password and get the count to 1, but then gets the right password, so we clear the state to get it back to 0. But in case the user misses a password, we enter the else block. This piece of code will look into the state and retrieve the current failures count. Note that the state variables come as a tuple, so it can be none in case there is nothing in the state variable, or a tuple that holds the value we want. That's why we need to retrieve the first value of the tuple to get the actual count. After retrieving the current failures count, we need to increment it. So what this line is doing is basically saying that if the user never missed the password, or in other words, if failed attempt is none, then it will be 1 from now on. And if the user has missed it once, it will be 2. If the user has missed it twice, it will be 3. Let me take out this print statement here because now you already know that it's an integer inside a tuple. We can see the update statement down here. When I type self.failattempts.update and pass a tuple with the value, I'm effectively updating the state of our application. Then, we're going to check when the user missed the password for the first time. In case the first error timestamp is none, it means this is the first error, and we set the request event time as the first error timestamp state variable. In case it is not known, we retrieve it and store it in the current first error timestamp variable. The last step is to check if the current failure count is bigger or equal to 3, and if the first error timestamp is bigger than 10 minutes ago. If both are true, we update the isBlocked state variable to be true. We are effectively blocking the user and will not process his requests anymore. We're also outputting a data frame with user ID and the block time. And this is our stateful processor. In the rest of the cell, We are just defining the input and the output schemas. Now, let's create our input table as a Delta table. As you can see, no user has missed a password until now. And finally, we're ready to trigger our streaming. We're going to stream from our recently created order table, group by user ID, and apply the transformWithState in pandas, passing our fraud detector processor class as the stateful processor, the output schema, the time mode, and an output mode. Then we start the streaming passing the checkpoint directory and calling the toTable method to write the outputs to a new table called block. While the streaming is running, we can go to our catalog and check the order and the block tables. Of course, the block table is empty now. Our streaming created it to be the output table, but as none of the user has missed the password more than 3 times in less than 10 minutes, we have nothing in the block table yet. Now let's create new data points. Let's make the user A to miss the password once and the user B to miss the password twice in a row. Let's append this new data to our source table so our streaming can process it. To see the logs, you can click in the cluster and select driver logs. We are looking for the standard error output. Here, we can see the logs of our application. We can see that rows is a generator. PDF is nothing more than a pandas data frame for each user ID or each key. And in this case, we are receiving one data frame for user B and another one for user A. We can also see the current failures for user B is at 2. And if we reload the page, we can see the current failures for user A is going to be 1. Okay, so now we can finally trigger a block. Let's say the user B misses the password again. Let's just append it to our source delta table and let's wait for a log update. So now we can see that user B has been blocked. We can also take a look at our block table and now we should see the block here. All right, that's working. Beautiful. But now there is one last and very important thing I would like to show you. The time to live attribute for state variables. Imagine that a user that is blocked or misses the password once just stops using our product or never comes back again. It would be in the application memory forever. And of course, it should not be a problem for our small application here, but for, say, a bank with millions of users, it will for sure be a problem at scale. That's why we will use the time to live feature. This is basically the time that a variable can live in the state. After that time, the variable will be cleaned up and will free our application memory. This memory handling is essential to keep our application running for longer periods and consuming the least amount of resources. And it's very easy to set time to live. Let's just create a variable called TTL in minutes and say 15 minutes. Also, let's change the checkpoint directory so we can restart our streaming from beginning. And as the third parameter of the get value state inside our stateful processor, I can set TTL duration ms, which stands for milliseconds, equals time to live in minutes times 60 times 1000. So this is our minutes to milliseconds conversion formula. I'll set it for all the 3 state variables, and here I'm going to change the time window to 1 minute and the time to live to 2 minutes, just so we can test it faster without the need to wait for 10 minutes to see it happening. Let's drop our tables to start over and rerun those cells to take effect before restarting our stream. And we got an error. If we go down here and look for the code of this error, we're going to see that to use time to live, we need to set time mode to processing time. Again, this is out of scope of this video, but if you really want to master real-time data streaming and be capable of managing those streams in production reliably at scale, you should spend some time taking a look at the time modes and other things that we didn't talk about here, that is watermarks. But this is for another video. Let's keep focused on what we have here. Let's just change time mode to processing time and restart the streaming. We can also force some misses for user B. Okay, as a result, we can already see that user B has been blocked because the order table already have 3 misses in a row. What happens if user B tries to buy something again? Let's send one more order for user B. So here's the result. User B is trying to buy something but is blocked. We didn't even process his order. That's working fine. We can see in the block table that user B was blocked at 8 p.m., 6 minutes, 37 seconds. So we expect user B to be free of this block 2 minutes later due to the time to live feature. And so let's wait some time and try again. And there it is. After 2 minutes, we can see that user B missed the password, which means that the order was processed and that user B is no longer blocked. The isBlocked state variable that was true became none after 2 minutes. And that's a wrap. I hope you enjoyed this look into stateful streaming in Spark. If you're interested, be sure to check out the official Spark 4.0 documentation for even more features. And if you have any question, please leave a comment. Thank you for being here and see you in the next lesson.